Okay, so when we tested the curl of this, this turned out to be 0. Uh, therefore, uh, this field is physically possible. And there exists a VR, okay, such that the gradient of this VR is equal to E, which means E has to equal to V integrated on some path dl. And so this is the x, y, z. Oh, let's switch this. E EDL equals to V. Okay, so the path of integration is arbitrary, which means we could go from 0 to say x, and then we can hold x and z constant just to make the integral simple, and go parallel to the y. So let's see here, and then we can hold x and y constant and go up to z. So x, y, z, and so this arbitrary point would be x, y, z. And then we can go on integrating each one of these paths. So v will equal e dl on path 1 plus e dl on path 2 plus e dl on path 3. And so if we start with path 1, on path 1 we know that y equals z equals 0. So is dy equal dz equals 0, because we know that dl is just dx in the I plus dy in the j plus dz in the k. And we know that x is x and dx is 1. So that means EDL here will be cx plus I plus zk plus yk, and this is dot product with dx, which is 1i, and so clearly these two go away and we get cx here on the first one, so it would be cx times 1, it would be cx. So this is on path number 1. On path number 2, we know that x equals x, we hold that constant, and y goes from 0 to y, and y goes from 0 to y. We know that z is 0, and we know that dx equals dz equals 0. Okay, so now EDL becomes on this path C xi plus vj. You don't have to choose the same path I've chosen. I've just chosen a convenient, easy path for my integration. Okay, and then we have 0 x plus dy and the 0 in the I. Oh no, sorry, x in the I. Well, it's dx. But dx is 0, so this is 0 in the I, yeah, and 0 in the dy, so this is dy in the j, and 0 in the k. Okay, so the only term that survives here is z, the j term, which is z dy in the dot product. Z dy. So if I integrate this path from 0 to y of z dy prime, I will get zy. And now I'll move to the third path. So the third path is going up to the z. So here we know that x is x, y is y, and z goes from 0 to z. So dx equals dy equals 0. We're not moving neither in the x nor in the y. And dz is just dz. So, no. So then EDL on this path, on path number 3 would be C xi plus vj plus yk dotted with 0 in the I plus 0 in the j plus infinitesimal amount in the z of z in the k, which is dz. So the only term that survives is the last term, which is y dz in the dot product. And so if I evaluate this on path 3, I will get y dz prime from 0 to z, and that will get me k, oh no, c, oh, I forgot the c here, so did I here? There was a c here, so this is cz1, okay, so c, so there's a c here, so this becomes cyz. And we already said that v is the integral, or actually there's a minus sign here. So v is the integral, negative the integral of EDL. So now I could go on to say that v is minus EDL from 0 to x, y, z. And we know that at 0 is 0, because we chose the 0 to be the point of origin. And so now I could just add the 3 paths, so I would get minus. The first path was, oh, I didn't do the integral. So the integral from the first path, dx, from 0 to x, is equal to cx squared over 2. So we get cx squared over 2 plus czy plus another czy, so this just makes it 2czy. So this, so our v in x, y, z will be this minus c to x squared over 2 plus 2zy. We can check this to see if it checks. We can evaluate the gradient of that because we know that e. So to check this, we know that e is equal minus the gradient of v, which I wrote here at the very top. I just forgot the minus sign. Okay, so if we were to evaluate that, this would make it the gradient. C times, let's keep the minus sign outside, d over dx of x squared over 2 plus 2zy in the I with d over dy of x squared over 2 plus 2zy in the j. In the j plus d over dz of x squared over 2 plus 2zy in the k. And then let's see if we actually do get the electric field back. So minus c, so this will give us an x in the I. And this will be 2z in the j, because the first partial derivative is 0. And the last one is 2. I'm getting a 2. Something isn't right. 3, see, okay. 3, The electric field was oh yeah, because here that's right. On path number one, Z is 0. So this guy turns out to be 0. Yeah, it's correct. I just didn't evaluate at Z equals 0. So this is 0. Let's see, on path number 2, no, path number 2 is correct. Path number 3 and path number 1 is also correct. Okay, so it's just path number 2 is 0. So that should make it 1, 3. Okay, makes sense. So, so we can remove this here. Okay, continuing on, we can remove all these 2's. There's only 1. Okay, so partial derivative with respect to y will be z. And partial derivative, the third one, will be y with respect to k. With respect to z will be y in the k. And so indeed, we do get the electric field back. That is minus minus, so this makes it plus, because the c is negative. So that means it checks. So this is how you could figure out the potential from the electric field along an arbitrary path.